Today we will discuss module 4, that is the crystal structures. The outline of the lecture is: first we discuss thermodynamic what are matters, then we define some basic definitions: space lattice, Dawes lattice, unit cell, primitive and non-primitive cell, types of crystal systems, lattice parameters, coordination number, and atomic packing factor. Miller indices and interplanar spacing, expression for interplanar spacing in terms of Miller indices. Then we discussed the directions and planes in the crystal system, Bragg's law and Bragg's spectrometer. Then we discussed the polymorphism and anatropy, and also discussed the structure and atomic packing factor of diamond. Finally, we discussed the perovskites. Now, we can say matter in universe is mainly classified into three kinds, that is solids, liquids, and gases. So in solids, all atoms or molecules are arranged in a fixed manner and have definite shape and size. For liquids and gases, atoms or molecules are not fixed and cannot form any shape and size. They gain the shape and size of the container. That's what I'm showing. Now, especially gases have atoms or molecules that do not bond to one another in a range of pressure, temperature, and volume. These molecules haven't any particular order and move freely within a container. For liquids, similar to gases, liquids haven't any atomic or molecular order and they assume the shape of the containers. Now, solids are again classified into two types. One is the crystalline solid and second is the non-crystalline or amorphous solids. Now we discuss what is a crystalline solid. A crystalline or crystal solid is a solid material whose constituent atoms or molecules or ions are arranged in an orderly, repeating pattern extending in all three spatial dimensions. So, a crystal is characterized by a regular arrangement of atoms or molecules. So, example, you can say for non-metallic crystals, ice, I can say carbon, diamond, sodium chloride, potassium chloride, etc. For metallic crystals, I can say copper, silver, aluminum, tungsten, magnesium, or etc. Now, this is the crystalline solid where atoms are arranged periodically in all three dimensions. For amorphous solid or non-crystalline solid, it is a composed of randomly oriented atoms or ions or molecules that do not form defined patterns or lattice structures. Amorphous materials have order only within a few atomic or molecular dimensions, and amorphous materials do not have any long-range order, but they have a varying degrees of short-range order. For example, for amorphous materials like amorphous silicon, plastic, and glasses. So, amorphous silicon can be used in solar cells and in thin film transistors. So, this is the atomic arrangement of a non-crystalline or amorphous solid. Now, we can basically classify these two, the crystalline and amorphous solids. The crystalline solid have a long range order, that is, they have a periodic array of atoms, and amorphous they don't have, they have only short range order. Example for crystalline, non-crystalline, I can say graphite and diamond are the best example I can quote. The physical properties of solid like mechanical, electrical, optical, etc. depends on the crystal structure. So, for example, below we see two crystal structures, that is graphite and diamond. They each contain only one kind of atom, that is carbon, but they exhibit strikingly different mechanical, electrical, and optical properties. The difference is now the difference in how these atoms are arranged inside the structure. Now we define some basic definitions. That is lattice point, the point in the space replacing the atoms in the structure of a crystal with a regular periodic arrangement and have identical environment with respect to other points are called as lattice points. These lattice points are used to study crystal geometry. Now we define what is the space lattice or crystal lattice. A geometrical representation of the crystal structure in terms of lattice points is called as space lattice. The distribution or placement of lattice points that surrounds any given lattice point remains same throughout the crystal. Arrays are arranged exactly in a periodic manner. Now we define what is the basis and unit cell. The basis, a group of atoms or molecules identical in composition, is called as the basis. Unit cell, the smallest component of the crystal, that is, it may be a group of atoms or ions or molecules which, when stacked together with pure translational repetition, reproduce the whole crystal. And the unit cell is the building block of a single crystal. And I can say a single crystal can have many unit cells. Now we can see how unit cell is arranged in a 2D. Now this is the unit cell arrangement in 3 dimension. Now we just study the 3 common unit cells in 3 dimension, that is the simple cubic, body centered cubic and face centered cubic. Now what is the crystal structure? Crystal structure can be obtained by attaching atoms, group of atoms or molecules which are called bases to the lattice sides of the lattice point. Hence, you can say crystal structure is real and space lattice is its geometrically equivalent. So this shows the how crystal structure will be formed. Same example. Now we define the Bravais or bracket. If a set of identical atoms or molecules are substituted in the space lattice, then the lattice is said to be Bravais lattice. Otherwise, it is said to be non-Bravais lattice. So, basis vectors we can represent a coded system. It is used to represent the position of lattice points in space lattice. Let A and B be two vectors having equal magnitudes and oriented along AB and AC respectively, as per the figure. With A and B as coordinate vectors, the position vector of any lattice point can be written as R equal to N1A plus N2B, where N1 and N2 are integers whose values depend upon the location of the lattice points with respect to the origin. Now we can represent in 3 dimension as R equal to N1A plus N2B plus N3C, where the terms are the residual units. Now we define what are the lattice parameters. The crystal's unit cell dimensions are defined by 6 numbers, that is, the length of the 3 axes A, B and C have 3 interaxial angles alpha, beta and gamma. To completely illustrate the crystal structure, the basic minimum parameters that required are the interatomic or intermolecular distance in x, y and z direction, that is ABC, and the angles alpha, beta, gamma between B and C, C and D, and A and B respectively. Now, these are 6 parameters, 3 translation vectors A, B and C, and 3 angles alpha, beta and gamma are called as lattice parameters. Now we define the primitive cell and non-primitive cell. A unit cell can be chosen in number of ways. The figure shows 2 ways of choosing a unit cell in 2 dimensions. In the first way, the unit cell contains lattice points only at the corner. This type of unit cells are called as primitive cells. In the second way, the unit cell contains lattice points in addition to the corners. These are known as non-primitive cells. And non-primitive cells are designed only for the sake of easy visualization of the symmetry in arrangements of the lattice points.